This is a follow-up lecture on ratio tests. Let's call it ratio test part 2. So in the last class, we talked about the ratio test as being this really important test for convergence for series. And I want to, just go through some additional problems involving the ratio test and then bring power series back into this. So this will be part of 10.5 when we follow up on the ratio test, and then also 10.6 where we start talking about power series, or these functions that are infinite series, power series. Okay, so a quick follow-up to last time. We could have these ratio tests. The ratio test basically said, if I want to understand what's happening with a series like this, then what I could do is I could, instead of looking at the series explicitly, I could look at a ratio of consecutive terms. And so I could look at a sub n plus 1 over a sub n. Oh, I don't like how this chalk is squeaking. Over a sub n, right? And look at that limit as n goes to infinity. And one of three things is going to happen, right? Either that limit is going to be less than 1, that limit is going to be greater than 1, or that limit is going to be equal to 1. Okay. So I look at these consecutive terms, I look at the ratio of consecutive terms, I look at the limit as n goes to infinity of that, and one of three things is going to happen. And if it's less than 1, then we have convergence. And when I say convergence, I mean convergence of the sum. Right? So if this ratio converges to some number less than 1, then the sum, the series, converges. Okay? In this case, we have a diverges. And then in this case, we have inconclusive. Right? We don't know what's going to happen in that case. Okay? And it really is then, ratio test is sort of a default way. As long as I meet certain conditions, it's a default way of understanding whether or not a series is going to converge or diverge. And when we move on to power functions, then it will, as I mentioned in class, answer most of the questions about the domain of a power function with the possibility of these sort of endpoints that we would then use the other tests to determine. Okay. So we could have something like this. A great example, sum n equals 0 to infinity of 1 over n vector. If we think about what's happening with a series like this, the terms, right? And the terms are the 1 over n factorial. The terms are getting closer and closer to 0, but as we've seen, that doesn't necessarily mean that the series will converge. Okay. So we could use a ratio test to try to understand this. Right? So my terms, a sub n, would be 1 over n factorial. And what I'm really doing is looking at a sub n plus 1 over a sub n. Okay? And so I will look at that ratio, and I want to try to understand, is that ratio getting close? What is that ratio doing? Is it converging to a number that's less than 1, greater than 1, or equal to 1? Okay. And as we saw before, a way that I answer that is I'll look at a sub n plus 1, which would be a 1 over n plus 1 factorial. Okay. And then instead of dividing by 1 over n factorial, I'll invert and multiply. So that'd be like an n factorial over 1. Just take the inverse of that, or the reciprocal of that. Okay. Okay. And something we're going to get used to, right, quite used to, is this idea of taking factorials and simplifying them. And we saw this in class on Monday, where if I have an n factorial over an n plus 1 factorial, that's like having an n times n plus minus 1 times n minus 2 all the way down to 1. And then the denominator would be like an n plus 1 times an n minus 1 times all the way down to 1. And all of these will cancel with those, leave a 1 in the numerator, and I could rewrite that as a 1 over n plus 1. Okay. Factorials, exponentials simplify nicely under this setting. Okay? And then with the ratio test here, basically it's saying since as n approaches infinity, I get something that looks like 1 over infinity, or it will converge to 0. And since 0 is less than 1, that tells me my series over here, whose terms are made up of these 1 over n factorials, converges. Now it doesn't tell me what it converges to, but it does tell me that that will converge. Okay. So there you go, right? So more or less we have examples that look like variations off of these things. Okay. It might be worthwhile, we're going to put this into, we'll talk about power series again here in a moment, but it might be good to understand why this works. Why does it, why would something like this work? Because if we can put it into a context, it hopefully will help us remember this. Okay. So, get rid of that, let's get rid of that. And roughly, whether or not it quite looks like this, the ratio test is a comparison test with a geometric series. Okay. The ratio test is really doing a comparison test with the geometric series. Because what we're saying is, when we look at a sub n plus 1 over a sub n, right, and we get as the limit some number rho, okay, right, get some number rho, let's write it this way, as n gets larger, these things are getting closer and closer and closer to rho. What is that telling me, right? Remember, again, whether or not a series converges or diverges is really dependent not so much on what happens in the smaller terms, but what's happening as n goes off to infinity. Okay? If those numbers are not getting small fast enough, then the series will diverge. And if they're getting small fast enough, then it could end up converging. Okay, so basically, it's saying as n gets larger, if this ratio is approximately rho, I'm going to rewrite it and just say, so more or less, for n being large, then my a sub n plus 1 is approximately equal to rho times a sub n. Okay. Right? That's saying that, you know, as n gets larger, that this number is more or less, just moving that up there, a multiple of that number right there. What multiple rho? Okay, which is more or less going to be like a rho times, this thing is more or less like a rho of absolute value a sub n minus 1. Okay, which is a rho squared a sub n minus 1. Okay, which is like saying this is more or less rho cubed times a sub n minus 2, right? And back to the beginning, more or less, I could say, you know, that something like this basically looks like, roughly looks like, a rho to n a sub 0, where a sub 0 would be the first term. Okay. Now, it doesn't mean exactly that, but that's sort of the idea that we have here, is that, you know, consecutive terms are basically proportional to the previous terms, especially as the terms get larger and larger and larger, and that's what's important. So we don't even have to take this all the way back to 0, we just have to take it back to some point and say, you know, things that look like that more or less look like that. So what that's saying is, let me put this in orange for a moment, is that if I wanted to sum up a series that looks like that, then more or less, this is going to look like some rho sub n a sub naught. Okay? And this is just some number, right? So I could pull it out. And so it'd be like taking a sub naught sum of rho sub n. And notice, this is just a number times what we call a geometric series. And we know about geometric series, right? Geometric series sometimes converge and sometimes diverge. And we know if the absolute value of rho is less than 1, then this thing will converge. And if we know the absolute value of rho is greater than or equal to 1, so it's converge up here, and it's diverge down here. And so, while it might not even seem like that's what we're doing here, we're doing a comparison test with a geometric series. And by saying this, we're able to make a statement that's sort of like this, okay? Which means that if I want to start summing those things up, then what I'm really doing is a comparison test. Say, well, those are really just behaving like this. Comparison, limit to comparison test, right? Which basically looks like that. And then just as a geometric series here. Okay. And since it's a geometric series, I understand geometric series converges in this case and diverges in that case. Now the thing that I don't know, right, so that's why I'm able to make a statement that, okay, if the thing I'm comparing it to is a geometric series where the rho is less than 1, it absolutely will converge. If I'm comparing it to a geometric series where the rho is greater than 1, it will absolutely diverge. And it turns out if I'm trying to compare it to a geometric series where the rho is equal to 1, okay, then I really can't say what's going to happen because it just kind of depends what sort of rho are we dealing with, right? I mean, not what sort of series are we dealing with. There'll be some cases when it's equal to 1 where it will converge. We've seen that before. And there will be some cases where it will diverge. We've seen that before. Okay. And if we need an example, we can always go back to our favorite, let's say, p-series, where we can say, oh, well, what about this guy, right? 1 over n equals 1 to infinity, which we know diverges. That's what's called the harmonic series. It's a p-series where p is equal to 1. That thing will diverge. But my a sub n over a sub n plus 1 over a sub n, okay, would look like a 1 over n times n plus 1 over, 1 over n plus 1 times n over 1, which would look like an n over n plus 1, which converges to 1. So there's a case where it converges to 1, and this diverges, right? So where the limit's 1, in this case, it diverges. Okay, and then I only have to square that. And then in this case, right, I get a sub n plus 1 over a sub n. Right? I'll get a 1 over n plus 1 squared times n squared over 1. Okay. I'll get an n squared over n plus 1 squared. And just as we saw in class on Monday, that limit is also equal to 1. Okay. And in this case, it converges. Right? Not because of the 1, but because this is a p-series, p is equal to 2. 2 is greater than 1. This one diverges because it's a p-series, p equal to 2. P equal to 1 diverges. Okay. Even though both of them, in terms of the ratio test, give me the exact same value, which is that one. Okay, so that's what happens, right? It just kind of depends. If the limit's equal to 1, what that's really telling me is that the relationship is not all that obvious, and I need to do something more than just compare. Like the rest of these terms here become more important. Okay. By the way, it also tells me why. I need to. Sorry, if I'm going to compare it to a geometric series. Why geometric series, like having powers of terms, is going to be so important in this. Okay, and then again, I can simplify such things, and same thing with factorials. I can simplify. I mean, it's a nice thing is when I have exponential terms and when I have factorials, it makes it easier to not get a 1. It makes it easier to get a number that's less than 1 or a number that's greater than 1. All right, so you've had some homework questions, you've gone through that. What I'm going to do is I'm going to sort of reset the board for a moment, and then I want to talk more about power functions. Okay? So I'm going to pause. Actually, you know what I'm going to do? I'm going to start a second video It's going to be another short video, and this will be, the second part of class for Wednesday, and then we'll talk about the ratio test in particular attached to the power series. Okay, so let me